Hi, chemistry students. Let's talk about the empirical gas laws. So let's break this down a bit. By gases, we're talking about molecules that act individually. They're not held together in clumps like liquids and solids, so they're not in the condensed phase. And so they move around independently of each other. And by empirical, what we're really saying here is that these are going to be laws or relationships between variables that are developed from experiment and experiment only. And that's what empirical means. The other option is to get an analytic solution by starting with a theory. But today this first video here is just going to be about empirical, the experiments that went on. And they were conducted by Boyle. So we're going to look at Boyle's law. They were also done by Charles and Gay-Lussac, which is now called Charles' law. And let's go look at these two experiments from the point of view of some simulations that kind of show us what happens. So here's Charles' law, and Charles' law is a relationship between what happens to a gas if we just change the temperature and let the volume change. So in this particular system, there's a constant pressure created by this weight. So the pressure inside and outside is always the same. All right, and it's always equal to whatever this is. So there's a constant pressure. The gas inside is not allowed to leak out, so there's going to be a constant number of moles. So the only thing that's going to be allowed to change is the temperature and the volume. So what I'm going to do is I'm going to set this to cool down, and we can watch what happens here on the graph. On the graph, you can see that as the temperature decreases, the volume also decreases. So these are in direct proportion because they're both changing in the same direction. And we can also say that this is a linear relationship because, well, as you see, it makes a straight line. So here we've got a linear and a proportional relationship for Charles's law. So what we'll do is we'll go back over here and we'll say, okay, for Charles's law, what we just found was the volume is proportional to the temperature. And just to remind you that this proportional means, that little symbol means proportional, means there's some relationship. We don't know exactly what it is, but as one goes up, the other one goes up. All right? So let's go back over here and we'll look at, instead, Boyle's law. And with Boyle's law, what we find is we can adjust here the pressure, we can adjust the volume and see how the pressure inside the container changes. So we're going to have a constant temperature in this case, and the number of moles of gas inside this little plunger here are going to be the same. So as it says, I'm just going to drag this, and we could have done this for any number of types of molecules. You get the same answer no matter which one you use. So I'm going to change this a bit. I'm just going to do this a few times so we can kind of see what kind of trends we get. Do a couple more at the very least. And then finally one last one where we go all the way to here. And just looking at the data, we can see in this data table that these are not directly proportional, but they're inversely proportional. Take a look. As the volume gets smaller, the pressure gets larger. So as one goes up, the other one goes down. That's inversely proportional. And on a graph, you can see that it shows up as the volume gets larger, the pressure is getting smaller. And it's nonlinear either. So that should tell us a little bit of something as well. So the end result is, for this particular one, we find that the volume is inversely proportional, 1 over P, for the pressure. So the volume and pressure are inversely proportional. That's Boyle's law. Avogadro, he did not do an experiment, but he made a hypothesis that said, you know, if I actually go ahead and increase the number of moles in my container, okay, if I increase the number of moles, I expect the volume to also increase. Why? Well, just like with the balloon, to blow it up, you just keep adding more and more molecules, and those push and make the actual balloon get bigger and bigger. So if we take these empirical laws, well, two are empirical, one's a hypothesis, we can build a new situation, a new relationship. We can say, all right, what we find is the volume is proportional to N, and it's also proportional to T, but it's inversely proportional to P. If we take these guys and we make them an equality by introducing an arbitrary constant, we get nRT over P, And then we can rearrange this one more step to get the ideal gas law, PV equals nRT, just by multiplying both sides by P. And you, of course, have seen this before. So R, in this case, is called the gas law constant. And we'll use it a couple of ways. It'll have different sets of units. It's 0.08206 liters times atmospheres divided by Kelvin and mole. Or it can also be equal to 8.314 joules per Kelvin mole. We'll get to that one later on. So there you have it. The empirical gas laws create this ideal gas law as it's become known now. And those all come from experiment.